Hello and welcome back to AP Pre-Calculus. Today's lesson 2.15 is semilog plots. So previously, we looked at the idea of using a logarithmically scaled axis to help us better understand the data. Because remember, the data in an exponential starts out really small. It's hard to see what those numbers actually are. And then all of a sudden it starts getting real big, real fast. And then we kind of would have to make a humongous X and Y axis to see it all. So sometimes it's better to look at it in a semilog plot to help us better understand the data, okay? So in a semilog plot, one of the axes will be logarithmically scaled. And in AP calculus, we're only going to do it to the y-axis. With semilog plots, this is the important stuff, like star this guy right here. With a semilog plot where the y-axis is logarithmically scaled, that's hard to say, exponential functions will appear linear. That's the important part. They like to throw this kind of question on the multiple choice on the AP test. They'll give you a couple of graphs and you have to pick out the right one, okay? So in an earlier lesson, we saw these graphs. This is the first time we saw it, right? We're going to formalize this and we're going to go into the semilog plot in a little bit more depth. We've talked about them already, but this is where we kind of mesh it out, okay? So look at what we got here. On the left-hand side, we have our normal linear X, linear Y, and these dots don't really mean anything to us. They're so close to the X-axis that we don't know what those are. And this 200 right here, well, that only gets us up to 1820. It's 2026. So we have to go another 200 years. Where do you think those dots would be now? Like, they're off the chart. We'd have to make this so much bigger. Whereas if we did it in a semilog plot, we could keep at it. We don't have to make our y-axis all that much bigger, okay? So notice how we have this nice growth idea here, but when we semilog this y-axis here, this is almost linear now. Like in the beginning, it's a little bit curvy, but look at that's a pretty straight line there. All right, so let's look at example 1 here. Use the features of the semilog plot above to justify why an exponential model is appropriate for the population of English Americans in the current United States from 1620 to 1820. Well, the reason is if we do a semilog plot with our data and the new graph looks fairly linear, then it was an appropriate model. So that's what we're going to write. So this is what I would write. A semilog plot is appropriate because the new graph appears linear. Okay. So example 2 has that other type of semilog plot written a little bit different. So we go up. This is 10 to the first, this is 10 to the second, this is 10 to the third, just like the other one, but they wrote them with 10. And each one of these lines from 1 to 10 count as 1. So this would be 2, 3, 4, 5, 6, 7, 8, 9, 10. But then from 10 to 100, they'd be 10. So this is 20, 30, 40, 50, 60, 70, 80, 90, then 100. And then from 100 to 1,000, now each line is 1,000, right? Okay, so example 2. After Mr. Passwater tells another one of his hilarious math jokes, it begins to spread around the school. The number of people P that have heard the joke after T minutes is graphed on the semilog plot above where the vertical axis has been logarithmically scaled. Which of the following functions could be a model for P? All right, so let's look at those lines. What do we notice about those lines that we have going on there? They look pretty linear, right? So if the semilog plot is linear, what do we know about our original function model? We know that it had to have been exponential. Knowing that, I can get rid of 2 of my answers right away. Which ones are not exponential? That guy and that guy. Cannot happen. So now we have to figure out which of these would give us, and really now I think it's just more of like a plug and chug type thing. So we have a input value. Like if you could tell me what that point was right there, it's going to help us out. So my input was 0 and my output was 2, right? Because the bottom number is 1. The next one up is 2. So which of these, when I put a 0 in for t, would give me 2? Well, if I put a 0 in right there, what is 2 to the 0 power? Well, it's 1. 2 plus 1 is 3, so it can't be that one. So D has to be answered, but let's just check real quick. If I put a 0 right there, what is 2 to the 0 power? Well, that's 1. And then I go 2 times 1 is 2. So there we go. It had to be this guy. Just a real quick note about semi-log plots. When we logarithmically scale the vertical axis for a semi-log plot, we are not changing the actual y values of the data, right? What we're doing is we are spacing them proportionally as opposed to linearly. So that's what makes that different, okay? All right, example 3. So reading through the question, I see the word semi-log plot, and I'm going to stop right there. I'm not even going to read the rest of the question. So I know that I'm trying to look at one of these graphs to see which one is a semi-log plot. And right away, I can look at A and B and go, it cannot be those answers because those are linearly scaled y-axis instead of proportionally scaled. Like proportionally scaled means we start out with a big wide gap and then they proportionally get smaller and smaller. They don't stay the same. So right off the bat, I'm getting rid of these guys, okay? So it's got to be B or D. So let's see what from here, I'm just going to plot the points, right? So I'm going to go to 1 on my x-axis. Here's 1. Well, the highest I go on this is 10, and it's telling me to go to 40. So guess what? It can't be that one either. But let's just check the other ones. Here, I'm at 1. That's 10, 20, 30, 40. That looks good. Then 2 to 60. That's 2, 10, 20, 30, 40, 50, 60. So it's definitely D. All right, so we've kind of done this before on one of our lessons, but let's do it again. We want to plot these points, all right? So let's start out with A, and we want to do 0, 200. So that's nice because 0 is one of the numbers on my x-axis, and I can find 200 on the y-axis. It is one of the lines. So remember, right here is 100, and then as I go up, every line will be another 100. So 200 would be this first line, okay? The next one, B, 125. So 1 is one of my X lines, so that's good. But 25 is not one of my Y lines. I have 20, I have 30, and a lot of people would think that we should put it right in the center, and it's really not going to make that much difference because it's so small. But let's think about this for a second. Is 50 in the center between 10 and 100? Let's go find 50. So here's 10, 20, 30, 40. You see how 50 is way up there? It's a lot closer to 100 than it is to 10. So that's because of the spacing. Well, the same idea goes on in between each of these guys. So 25 is going to be closer to 30 than it is to 20. So we really should be putting it a little bit higher than midway. Not that we can really make a difference on a small graph like this, but we do have to understand the concept that the spacing in between is proportional, not linear. 0.5 is not in the middle of 0 and 1, okay? 2, 7, let's do C. 2, 7. Well, 2 is a good number, 7 is a good number. So there's 2. This, if I was right here, this would be 2, 1, 2, 2, 3, 4, 5, 6, 7. So we got to, I got to be able to see which one is 7. I think that one was 7. Again, hard to see. Uh-oh, D is 3.2. 3.2 is not on one of my numbers, but they gave me these awesome dashes, and there's, to get from 3 to 4, they cut it into fifths, which is 0.2s. So I'm going to be right here on this dash, and 800 is one of my numbers, so I got to go up here. I believe that's 800 right there. And then last but not least, 4.6, I got to go over 3 dashes. So we would go to this dash right there. 1.5, same idea. Right on the line would be 1. So I want to go up to 2. I'm going to be a little bit closer to 2 than I am to the middle, okay? That's how those go. Okay, as we've seen, if we have an exponential function and then we do a semi-log plot, it will appear to be linear. In these cases, we can create a linear model for the graph on the semi-log plot. Like if we have the original data, we could do an exponential regression and do that. But what if I wanted that linear model? Okay, so remember, I'm going to do it down here. Y equals a to the bx. We want to take the log of our y answers, and the right hand side is the answer. So really, I want to do this: log of a bx. Well, let's expand that. So I could do log of a plus, and remember that x is going to come down, x log of b. Okay. So what does that kind of look like there? That kind of looks like y equals mx plus b, because log of a number is just a number, right? So this is just a number. Whenever I put a number in for b, it just represents a number, and it's with the x, so that means that's the slope, and log of a would be my y-intercept. So you'll notice up in their notes, they used ends down here. I didn't really put anything because for the most part, when we do a semi-log plot, we're going to do base 10, but you can do any base you want. I guess you could do 3s and do 3 to the first, 3 to the second, 3. I guess. I don't know why you do that, but you could. All right. But for most of the time, we're just going to use 10s down here. So this right here would be our linear model for the semi-log plot. We would have a exponential model for our exponential graph, but this would be the linear graph that goes with those weird semi-log plots. All right, for example 5, we have a semi-log plot up there. Luckily for us, it is in base 10, and remember, it's almost always going to be a base 10. What do you notice about the dots there? What do they form? Those points seem to make a pretty good line right there. So we could come up with the formula for that line. And what do all lines have? Well, they have a slope and a y-intercept. So that's what we're going to have to figure out. And how do we find slope? What is another name for slope? Average rate of change. So I could take any 2 points and I could do my slope, because that's just an algebra slope, right? So let's pick 2 points. Let me get rid of this pink line real quick. All right, let's pick these 2 points right here. So 1 and 2, right? Now, we got to be careful because we did a logarithmic change on the y-axis. So we don't really have, like if we look at this point right here, 10, 20, 30, it's 40, but it's not really 40 because those numbers are all logged. So we would do log of 40. And the next one, if you count it up there, you'd get log of 60. So when we do our average rate of change, we do log of 60 minus log of 40 over 2 minus 1. And that will give us 0.17609125991. I just wrote everything that was on my thing because if I'm going to use the slope, if I'm going to use this number, I don't want to round it here because they might take off for the rounding error. Okay. So let's look what our line looks like so far. We're used to being y equals mx plus b, right? So y equals 0.17609125991x plus b, our y-intercept, right? But our y-intercept is on the y-axis and it has been logged, so I want to do log of whatever that is, right? So that's the weird part about this, because you got to remember that our y-axis has been logged. So we have to log anything that is dealing with the y. So how are we going to get this? Well, back in the day when it was just y equals mx plus b and we found our slope, we would pick a point and substitute in the x and the y. Well, guess what? We're doing the same thing here that we did there. So we could pick either one. I'm going to pick the first one, right? So y was log of 40. And when I put a 1 in for x, I get 0.17609125991 plus log of a. So now we have to move that big long decimal over, and it should be saved in your calculator because you just did it. So if you just take your calculator and do log 40 minus, and then arrow up to that long decimal and hit enter, it'll do it for you, and you'll get what log of a equals, okay? And that equals, so now let's write our linear model out. So we have y equals, and now we can round because we have our good numbers here. So 0.1761x plus 1.4260, right? There you go. All right, finishing up on this, we're on B here. So we're going to use the linear model that we just had in part A, and we're going to rewrite it back to its exponential model. So I need to find the A and the B. So I have the A and the B, right? So I have A right there, this big, long, nasty number. I have B right here, the slope, right? This is the B. But those have been logarithmically changed. So I need to change them back. What was my base that I used in my semi-log plot? Well, it was base 10. So I can take A, say base 10, and take that long, nasty number that we had for A, 1.425968732, and just put that into our calculator, and we're going to get A equals 26.6 repeating, so we'll go out 4 decimal places, right? And then we do the same thing with B. We go B equals 10 to the, and then we use this long 0.176091259, and we put that in our calculator, and we get a much nicer number of 1.5. So to finish the question, we just got to write out the formula. Y equals, my A was 26.6667 times 1.5 to the x. And there is my exponential model that would have been good, that went along with my semi-log plot linear model.